speaker is Ben from University of Oxford, and he will talk about range avoidance and whatever.
Thank you. So I'm going to talk about range avoidance and hard partial truth tables. Unfortunately, I don't have time for remote point today. If you want to talk about remote points, you can come to me offline. And this is a joint work with my lovely cousins. They are Ye Yuan from Xi'an Jiaotong University, Yi Zhi from Tsinghua University, and Jia Tu also from Tsinghua University. They are very talented and hardworking young researchers. So also, I didn't find a photo of Ye Yuan, but please believe me, he's very handsome. So another very important point I want to emphasize is they are senior undergraduate students and they are applying for PhD. So if you see their name on your application pool, please accept their application. Yeah, you can forget about what I'll mention later, but please remember this slide. Thanks. And now let me start by mentioning something deceptively simple. Maybe I can say this. That is prove a law bound for CNF. So you probably know that CNF is this class of depth 2 circuits where at the top you have an AND gate. Oh, by the way, if you have any question, please feel free to interrupt me. So on the top you have an AND gate of unbounded fan-in, and on the bottom you have OR gates. So this looks like an easy question, right? If you have some function called parity, then you know it is hard for CNF. Actually, it's exponentially hard. And you even understand the optimal CNF for parity because like each zero in the truth table of parity requires one OR gate at the bottom. So the optimal size is 2 to n-1. So anyway, that's not important. I'm just illustrating that you have a very good understanding of this circuit class seemingly. But what about when you are only given a partial input set? So here is the question. I have a table where on the left-hand side, I have some inputs, and on the right-hand side, I have question marks. I want to replace each question mark by a bit 0 or 1, such that what I get is a partial function that is hard for CNF circuits. If this doesn't make sense, then I have my next slide has a slightly more formal definition of this. So, so this is a computational problem where you get as input L strings of length n. And you can think of L as something between poly n and the 2 to n. And for concreteness, think of it as sub-exponential in n. Your output will be bits y1 up to yl, which are bits used to fill in the question marks. And the requirement is that the partial function from xi to yi you get will be hard for CNF formulas, which means for any CNF formula of poly n sides, there exists some I such that C fails to compute fails to map xi to yi. So is this definition clear?
Xi need to be distinct, I guess.
Yes.
It is called an I checker.
And maybe some version of definition you can come up with your xi, but now we are in a hard mode, so the adversary gives you xi. So this question, when you first look at this question, you may think parity is hard for CNF, so maybe parity will remain hard on this partial function. So we can just plug in the results of parity here, but then you realize, oh, sorry.
So for certain short lists, there's, obviously, you're saying L is big. So
yeah,
this will always have a solution.
Yes, I'll talk about that later. Thanks. And so So you feel in parity here, but you after a while you realize there's a problem. If I give you the set of inputs where parity becomes 0, then you will give me the all 0 function, which has a trivial CNF circuit. So this problem is not as trivial as you think. And actually it's open. We don't know if this problem has a non-trivial polynomial time solution. Of course, I mean deterministic polynomial time. Any questions?
Is this a decision problem or is it a function?
Oh, it's a search problem or function problem. You will need to output a lot of bits. Like
Sometimes the answer is no.
No, when L is big like that, there's always going to be some.
yes.
No, but then I don't get the solution. What is the problem? I'm given the list, I'm given the xi's and the yi's, and I want to output.
No, you're given the xi's.
Yeah.
I'm not given the yi's?
No,
not.
you're supposed to find
So
the
we are
yi's
switching.
so that it's a hard.
I'm supposed to output the words so as to make it a hard problem.
So the problem name is hard partial traceable. The input of this problem is strings xi, and the output you need to find are the bits yi, such that the partial function becomes hard for CNF circuit.
So by hard, you can just make it like square root of L, it needs square root of L size.
You mean the
poly
hard? Yeah, you can fix some circuit size which should be smaller than L.
Polylog.
Is there a relation to other promise kind problems for AC0 or AC or CNF? Like, for instance, computing parties. We know that CNF or AC0 cannot compute party, but now it's open whether you can compute by AC0 and possibly even by CNF. For some set of parties that does not trivially span the parity of all inputs, it's open whether you can compute, whether there exists a set of parties that do not span the parity of all inputs, and yet it's hard for CNF to compute party from parties. So this is
sorry
just
to interrupt this discussion, but we should let Hanlin talk. These questions will be
Okay.
answered in the talk, so
Okay.
after a while.
okay. I'll take it off.
I think yours question we can take it offline. And
Sorry, but I just have a quick clarification about the problem. So, it's not, should it be clear to us that there always exists such a Y1 through YL?
yes, and I'll actually present proof. I mean, L is much larger than the poly size here. Like L is 2 to the square root n, but the size parameter is only poly n. If this is the case, then you can prove there always exists a solution.
Because there are 2 to the L possible functions.
Right.
Oh, you are spoiling my slides.
Try quickly. Yes. That's why I interrupted this.
I just want to mention that this problem was defined by Alvin and Sikans, who is here. Well, they have some other motivation in complexity theory, but I think this problem itself is an interesting problem. And it's also frustrating that we know a lot about CNF, but we still cannot solve this problem. In this work, we solve this problem for ACC0 circuits, but our algorithm needs an NP code. So if you don't know what ACC0 circuit is, then it's fine because you don't need it in this work, in this talk. But it's some circuit class that's much stronger than CNF, and it's in some sense a frontier class in current circular bounds. So now let me address the question that many of you are concerned with. Why is there a solution at all? Let's say there are L inputs, and you require harness against size S circuits. If L is less than S, let's say much less than S, then there's no solution. You can always like hard code all of the answers by a CNF of size slightly larger than L. But if L is greater than S, then there exists a solution, and it can be proved by the probabilistic method. Because the proof is important, I'll go through it. So there are only like roughly 2 to as many circuits. So these are circuits. Maybe it's not clearly shown. You can see from there. But there are like 2 to L possible partial functions because each question mark has 2 possible choices. So each circuit can only give you 1 partial function. So there are always some partial functions that are not mapped. So if L is much larger than S, then there has to be some partial function not computed by any circuit, and your task is just to pick out such a partial function. If I ask you again, why is there a solution? You might answer the answer is the empty pigeonhole principle. What is the empty pigeonhole principle? If you are if you throw n pigeons into m holes, where n is less than m, you throw n pigeons into m holes in some arbitrary way, and n is less than m, then there has to be an empty pigeonhole. Actually, there has to be at least m minus n empty pigeonholes. In this talk, let's consider the weak version where, let's say, n is much less than m. Let's say n is less than m over 2. So you can see that what guarantees a solution in the hard partial traceable problem is exactly this empty pigeonhole principle. And now let me introduce the main subject in this talk. That is the range avoidance problem. In this problem, you are given as input a circuit from n bits to L bits, where L is greater than n. And you want to find some string y that's not in the range of C. So for any x, Cx is not equal to y, and we will call this y a non-output of C. So this problem corresponds to the weak empty pigeonhole principle. You can think of the circuit C as it maps a pigeon into a hole. So there are 2 to n pigeons and there are 2 to L holes. Given the index of a pigeon, C tells you how to map it to a hole, and you just want to find an empty hole. So I'll give you some examples on why this is the problem that corresponds to like a weak empty pigeonhole principle. But now I also want to remark that this is the white box version of the missing string problem that Ryan just discussed this morning. And this problem has a trivial randomized algorithm because you can see like most strings are non-outputs of C. So you can just output a random string and wish that it works. But we are really interested in deterministic algorithms for this problem. So let me illustrate that range avoidance corresponds to weak empty pigeonhole principle by giving a reduction from hard partial true stable to range avoidance. If you still remember what hard partial true stable is, the input is a list of input strings, and the right-hand side of this table is not filled yet. Now we reduce it to the following instance of range avoidance. Note that each instance is a stretching circuit. So the input of this instance is the description of a DNF circuit C, which only takes like 3s log s bits. And the output is the right-hand side that this C maps to. So it's the concatenation of Cx1 up to Cxl. If 3s log s is less than L, then there has to be a solution. And any questions? And if you find a non-output of this circuit, then you plug it back here and you get a hard partial true stable. Is everything clear? Yeah, so this is exactly what was happening in our so-called probabilistic method proof. And what this circuit does is it maps this circuit to the true stable. So you can see that I mentioned two things before. The first thing is the existence of a solution is granted by the weak empty pigeonhole principle. And the second thing is that the search problem is reducible to range avoidance. And they are the same thing. In general, there is a phenomenon of explicit constructions. And there are some property P that people are interested in. And you can use the weak empty pigeonhole principle to show that a random object satisfies P with high probability. And on the other hand, it's very hard to deterministically construct any string, any object that satisfies P. Some infamous examples are hard truth tables, where some people call it circular bounds. Rigid matrices and Ramsey graphs. If you don't know about the latter two, it's okay because I'll just illustrate them as examples. In a very nice paper by Oliver Cotton, he showed that range avoidance is this problem that captures explicit constructions in the sense that for all these natural explicit construction problems, you can reduce it to range avoidance. So if you can solve range avoidance, then you can solve all these explicit construction problems. And moreover, the reduction itself is essentially the proof by the probabilistic method. So for example, to find a hard truth table, you just need to do the range avoidance for the so-called truth table generator. This generator takes as input a small circuit and then expands the circuit into its truth table and outputs the truth table. So if you have an output of this generator, then you have a hard function. And the other examples I don't have time to define here. Now let me look into what has happened in circular bounds and see if they will give insights on general explicit constructions and range avoidance. In a decade ago, Ryan, it's you again. Yeah, around a decade ago, Ryan proved this breakthrough result that NEXP is not in ACC0. Here, again, ACC0 is this frontier circuit class, and we don't know how to prove ACC0 lower bound by other ways. What's nice about this proof is that it has two steps. The first step, you have Ryan showed there's a so-called non-trivial algorithm for so-called CAPP for ACC0. I'll try to explain what it means. But later, but the second step is he also showed such an algorithm implies circular bounds. So what is CAPP? CAPP is this circuit acceptance probability problem. Your input to CAPP is some circuit C, a single output circuit C, and you want to estimate the probability that C accepts a random input with additive error, let's say constant. It's clear that there are trivial algorithms for CAPP. The first trivial algorithm is you just sample a bunch of random inputs and test C against this random inputs. So this is a poly-n randomized algorithm. And the second algorithm is you just do brute force. You enumerate through all inputs. It's 2 to n poly-n deterministic time. Non-trivial algorithm means you need to beat the trivial deterministic algorithm. So you want to run in time slightly less than 2 to n time. And it's impressive that even this very marginal improvement over the trivial brute force algorithm gives you some circular bound. And this connection is very general. Ryan actually showed that for any typical circuit class C, if you have a non-trivial algorithm for CAPP problem of C, here your input is a C circuit. If you have a non-trivial algorithm for CAPP of C, then NEXP is not contained in C. In this talk, let's use this slightly weaker bound that E to NP is not in C. E to NP not in C corresponds to polynomial time algorithm for range avoidance with NP oracle. So let's recall this true stable generator. It takes this description of an ACC0 circuit C and maps it to a true stable. So what Ryan proved, it's essentially that the range avoidance problem for this specific true stable generator has an unconditional FP to NP algorithm. To see why it holds, like you first notice that the true stable generator, the output length is 2 to the n, and therefore polynomial time algorithm for range avoidance becomes exponential time algorithm for constructing a hard true stable. So this naturally leads to the following questions. Is there anything special about true stable generators, and can we do like general range avoidance? This was the motivating question when I was when I started doing this project. We wanted to generalize the algorithmic method to general range avoidance problem.
Sorry, when you say in the previous slide, when you say for this specific range avoidance, this actually holds. So for any ACC0 circuit, I can do the range avoidance, right?
No,
no.
I'm just saying for this specific generator, the generator takes as input an ACC0 circuit and outputs the true stable of the ACC0 circuit.
So you're
there's
saying
only one generator.
But you're saying if I give a generic ACC0 circuit, you cannot solve range avoidance?
Yeah, that's our new result.
Oh, okay, all right, thanks.
So is this function C0 because you need to have like a universal ACC0 evaluator?
Good point. For ACC0, I believe it's still in ACC0. For some not very typical class like ACC0 threshold, maybe you cannot do that. I'm not sure.
But like depth 5,
You have to fix
ACC0.
it, yeah.
Yes. So if this input has depth D, then maybe this circuit has depth larger than D, maybe 2D or something. I don't know. So in a previous paper with Rahul, who is also here, and Zhikun, who is another undergraduate student, we got some algorithm method for range avoidance. We showed that something called non-trivial Hanlin weight estimation data structures imply FP to NP algorithm for range avoidance. Let me explain what this data structure is. The data structure receives a circuit for preprocessing. The circuit has more outputs than inputs. It has a preprocessing phase and a query phase. During the preprocessing phase, you receive the circuit, you compute the data structure, you have NP oracle. And in the query phase, you are given an input of this circuit. You want to estimate the Hamming weight of Cx. That is, estimate how many output bits are 1 given this input. But you want to do it in non-trivial query time, which means deterministic time less than L. L is the output length. Of course, you have oracle access to the data structure. Otherwise, I think it's impossible for general C. You can see that CAPP is indeed Hamming weight estimation for the true stable generator. To see why, what is the Hamming weight estimation problem for TT? It's during a query, you are given an input X, which is a circuit. You want to estimate the Hamming weight of the true stable of the circuit, which is estimate the probability that the circuit outputs 1 on a random input. So hopefully this is clear, and this result is a generalization of Ryan's algorithmic method. Any questions?
What is the generalization here? So you invoke a new data structure. I'm trying to understand what is the generalization here. You invoke a new data structure, and then you characterize the properties of this data structure so you get the same CAPP.
No, I just mean Ryan's lower bound is a special case of this new result, because if you plug in C being the traceable generator, then you just need to solve CAPP in order to find the non-total of C. I made a slide to compare these two results. The algorithmic method says that non-trivial algorithms running in this much time for CAPP implies circular bounds, and our result says non-trivial data structures running in this much query time with some PTNP preprocessing for Hamming weight estimation of C implies FP2NP algorithm for range avoidance.
Is this the P to the NP preprocessing?
Or this is one difference, and another difference is we can deal with arbitrary circuits, like arbitrary input of range avoidance.
Sorry, and your conclusion in the last slide, does it imply circular overbound?
Could you say it again?
Your conclusion at the bottom rightmost
This
square,
algorithm for avoidance?
does this imply circular overbound?
If you can implement traceable generator in this class C, like traceable generator for another circuit class for in this C, then it implies circular bound. Does this answer your question?
Okay. So and can you do it for classes like the ones for the algorithmic method, like ACC0 and the other ones?
We can do ACC0, but I don't know if we can do ACC0 threshold, because that doesn't seem to be universal.
So you're saying in terms of actual applications, what you're getting is actually weaker in terms of lower bounds for circuits. You get other things, but for circuit lower bounds, it's not quite as general as the algorithmic method. Is that what you're saying?
Could you repeat the question?
In terms of circuit lower bounds, you're saying that the current applications of your techniques are weaker than what we know with the algorithmic method? Is that what you're saying or not?
Maybe you still need a universality.
Okay. So, okay.
Thanks for the question.
For the algorithmic method, you also need universality of the class, or no?
I don't think so.
Like bypass by the circuit, and that should be universal. Oh, wet of them.
Okay. So one drawback of the previous paper ISW is that Hamming weight estimation appears to be hard, and we didn't get very good unconditional results. In the new paper, we showed that non-trivial algorithms for satisfying pairs, which is another problem, also imply FP2NP algorithm for range avoidance. So what is satisfying pairs? It's not a data structure problem. It's just a static problem. The input consists of n circuits and m inputs. For now, think of the capital N and capital M being much larger than circuit size and input size. What you want to do is to estimate the number of ij such that Ci of xj is 1. You can see that this is in some sense an offline version of Hamming weight estimation. This C circuits gives you a multi-output circuit. I mean, this n circuits, you can think of it as one multi-output circuit, and the inputs in Hamming weight estimation, they are given in an online fashion, but here you just get a batch of inputs. And instead of outputting the Hamming weight for each C of xi, you just need the average Hamming weight. So actually, okay, so this is satisfying pair problem. Any questions?
So this capital N is like L in the last slide. L in the
I guess so. And you can think of it as you have a table where rows are circuits and the columns are inputs. The entry is 1 if the circuit accepts the input and is 0 otherwise. You want to estimate the fraction of entries that is 1. But you want to do it in non-trivial time, which means you don't have time to construct the whole table. Well, your impedance is roughly n plus m, but the table size is nm, so you want to beat this trivial nm time. Also, you can use some kind of meter in the middle to show CAPP reduces to 2 to n over 2 circuits and 2 to n over 2 inputs satisfying pairs. So a non-trivial satisfying pair implies non-trivial CAPP. And we also observe that. Yeah.
Row equal and you said verbally reduces. Satisfying pairs harder, or is it actually equivalent?
I don't think it's equivalent. By reduces to, I actually mean like non-trivial algorithm for CAPP reduces to non-trivial algorithm for satisfying pairs because the reduction is 2 to n over 2 times.
So the way you would do the reduction is to, let's say, pick the first n over 2 variables.
Yes.
And set them in all ways and restrict the circuit, the single circuit in all 2 to the n over 2 ways to create your family. But that's a very uniform family, whereas the general satisfying pairs problem involves circuits that might be totally unrelated.
Yes, that's true.
So is that the main difference? Why there isn't like an equivalence?
On the other hand, the input length of CAPP is just circuit size. But impedance for satisfying pairs is like capital N plus capital M. It's like square root of the brute force time. So I don't think these two problems are equivalent. And we also observed that implicit in previous work was a non-trivial algorithm for ACC0 satisfying pairs. So we just plug in this algorithm to our framework, we get an FP to NP algorithm for ACC0 range avoidance. So there's I omitted the parameter setting, like what's the circuit size and what's the stretch. Just think of if some like non-trivial parameter setting for which the FP to NP algorithm works. And this result also recovers the best ACC0 circular bounds because our result is a generalization of the previous result and uses I mean,
Don't you use like that lower bound to get your algorithm?
yeah, we at least use your techniques and maybe plus some new things.
Yeah.
And come back to the partial stable problem. We can use this range avoidance result to show there's an FP to NP algorithm that on input the domain of a partial truth table and fills this partial truth table so that it's hard against the ACC0 circuits. Again, I didn't mention for which parameter region. But for some non-trivial regime, it's doable. There are two proofs. The first proof is to use universality of ACC0 and directly reduce this to ACC0 avoidance. Second proof is you don't need universality in this case, and you can run this algorithmic method again. What you get is non-trivial algorithm for C satisfying pairs imply FP to NP algorithm for C hard partial truth table. And this doesn't need universality. Okay, am I going a little bit fast? What's the time now?
Have about 9 minutes or maybe 10 minutes.
Oh, thanks. So let me promote an open question that I really want to see it solved. The problem is to solve the NC03 range avoidance in FP to NP with maybe a small polynomial stretch. What is NC03? NC03 is the class of multi-output circuits where each output bit depends on only 3 input bits. So it's very local, like every output bit can be computed locally, like by only looking at 3 input bits. But it's non-uniform NC03, so the wires might be like arbitrary. Previously, a very interesting paper by Wang, Wang, Xinlu, and Sohan Wang showed that stretch n square for NC03 circuit, you can solve stretch n square in FP to NP. They didn't use algorithmic method. I believe they used some like Fourier analysis maybe. Anyway, but I was thinking that n to the 1.01 might be approachable, but now I don't know.
0, 3, you have only 2 layers, or is it just constant number of layers?
If it's NC0, then each output bit only depends on constant number of input bits, and it doesn't matter how many layers there are. And this 3 here just indicates the locality.
Is there any intuition for like what's like y and s squared maybe have another?
Oh, sorry, I actually don't know how this algorithm works. So it suffices to solve the following, again, innocent looking hypergraph problem. Your input is a 7 uniform hypergraph consisting of little n vertices, capital N hyperedges. You are also given some cuts. So a hypergraph is just a set of vertices and a set of hyperedges. 7 uniform means each hyperedge contains exactly 7 vertices. Like there are, I think I draw 4 hyperedges. A cut is some way to partition the vertices into 2 parts. And we say a cut goes through an edge if the edge intersects both parts of the cut. So this cut goes through the orange edge, also goes through the blue edge, but it doesn't go through the purple edge and the green edge. I hope this makes sense. And you want to estimate the number of ij such that the jth cut goes through the ith hyperedge. So, and you, I didn't mention non-trivial time. I'm sorry. I see. Thanks. So, if you can solve this innocent-looking hypergraph problem in non-trivial deterministic time, then you get a good algorithm for NC03 range avoidance. And you can probably see this is just a variant of NC0 satisfying pairs. And one point I didn't mention is like our ACC0 avoidance algorithm only works for quasi-polynomial stretch. So the number of if there are like n inputs, then there should be like 2 polylog n outputs in order for our algorithm to work. So the ACC0 avoidance algorithm doesn't help to solve the NC0 avoidance here, because
so this problem, you have an input, you're supposed to output it, and the question is, can you do it in what? What is you have defined the problem here. What is the question? Can you do it in
It's right
what
above
resources?
NFP
to the NP.
Wait, I have 2 problems here. First is the NC03 avoid. The second is the hypergraph problem. Which problem are you talking about?
The second one.
Oh, so you are just given this hypergraph and cut, and you want to estimate the number of pairs.
Over
Yeah.
Okay. And over long times and
NM, trivial algorithm runs in roughly NM time, and you want to shape
times NM appears twice.
Oh, it's you need to shape some log factor here. So maybe I should add a parenthesis on this log omega 1 nm.
The log is of nm. So.
Ah.
Okay.
So the n to the 100 is the same as the 1.1, the 0.01 and the 100?
Maybe not. I haven't calculated the parameters. Maybe it just means your FPGA algorithm takes n to 100 times. Oh, so n to 1.01 should be this thing, I guess.
Is this equivalent or it suffices to show this?
It suffices. I want to prove it's equivalent, but I'm stuck.
The connection with that problem equally applies for like an 04 or
Yes, but the uniformity might be higher.
okay, 15, just some larger constant.
Not 15, maybe just 2 times 4 plus something, because we have like NC2 or NC3 overhead.
Yeah.
So it's not 2 to the power of 4, instead it's 2 times 4.
Even better.
Hopefully. So if everything is clear, let me jump to my final slide. There's a summary of this talk. I introduced this range avoidance problem, which is in some sense characterizes the dual-weak pigeonhole principle. And if you solve this problem, you will have dramatic consequence in explicit construction. And to solve this problem in FP2NP, it suffices to solve something called satisfying pairs by a non-trivial algorithm. And finally, this has some application to the hard partial truth table problem. We can solve this problem with an NP oracle, but without NP oracle, it seems to be completely open. And that's all for today. Thank you.
Can you solve it for something deeper, like monotone DNF?
I don't know. I remember Jatu investigated this somehow. Maybe I don't know. I think it's either equivalent to some non-monotone variant or it has trivial solution.
Any connections between range avoidance for different classes? Like any connections between range avoidance for different classes, non-trivial connections, like NC03 and NC010? Do you know any?
Oh, nice question. We have in the small stretch regime, we have a reduction from NC1 avoid to NC0 avoid. So small stretch means you map from n bits to n+1 bits. Which means for this open question, if you can solve it for n+1 stretch, then you prove E to NP require exponential size formulas, which would be very strong. But as far as I know, for larger stretch, there's no dramatic consequence.
It's the same issues as with stretch for low complexity PRGs. Like,
yes.
I said it's the same issues here as with low complexity PRGs, like NC0 PRGs, but having stretch n to 1 plus epsilon versus having stretch that's small. Small stretch is equal to NC1.
Yeah, even the proof techniques are the same.
Yeah. Thanks.
More questions?
Yeah, so like for AC0 and these other classes, you have better set algorithms. Does this just improve like the stretch for which you can solve avoidance, or does it actually help you algorithmically?
I think it just improves the stretch. Although in our framework, we didn't get very tight about stretch.
Yes. I imagine that you can work with like lower stretches.
Yeah.
Three avoid algorithm for stretch n to the 1 plus n to the 1.01 stretch. Yeah, this slide. Like if you solve NC03 avoid for this stretch, then does it imply any explicit constructions for n to the 1.01?
I don't know. It's just out of curiosity. Actually, many explicit constructions reduce to range avoidance, but only in small stretch regime. It's a very nice research question. Like, can you solve it in small stretch regime?
Okay.
Consider with RT3. If it's RT2, it's a corresponding point of universal.
If it's already 2, then GLW paper solved it even with stretch n+1, and it's in polynomial time without NPL alpha.
Does that also imply an algorithm for the satisfied pair?
I don't think so. Actually, satisfying pair also gives you remote point algorithm, and I believe NC02 remote point is open.
I had a question.
Yeah.
Would you say just one sentence what you skip? You skipped one part.
Remote point? Yeah. So you want to find some string whose Hamming weight is far from any string in the range of circuits. So that's the remote point problem. You can still prove by probabilistic argument that this string exists. And a good enough satisfying pair algorithm gives you a FPGA algorithm for remote point.
Okay, so thank you again.